In episode 34, Apply Secure Coding Fundamentals Across Languages and Stacks, we focus on the everyday coding habits that prevent entire classes of bugs before they become defects, incidents, or exam questions. Secure coding is not a matter of mastering thousands of edge cases. It is about adopting habits that apply across languages, frameworks, and architectures. These habits reinforce predictable behavior, reduce the chances of dangerous surprises, and create guardrails that hold up even when teams are moving quickly. When you practice these fundamentals consistently, your code becomes easier to reason about, review, and defend. The goal is to build assurance into the daily act of writing software. A reliable first step is to prefer safe, well-maintained libraries instead of reinventing complex functionality like cryptography, parsing, or serialization. Cryptographic functions are notoriously easy to implement incorrectly, with subtle mistakes leading to profound vulnerabilities. Parsing and serialization logic can be equally fragile, creating opportunities for injection, memory corruption, or malformed object attacks when implemented casually. Mature libraries benefit from years of testing, community inspection, and hardened implementation choices that individual developers cannot easily replicate. Choosing existing, reputable components reduces risk and allows you to focus on business logic instead of resolving intricate security problems. Input validation, canonicalization, and strict type handling form the next layer of defense, ensuring that your code treats external data as untrusted until proven otherwise. Validation checks formats, lengths, ranges, and known structures, blocking malformed or malicious input at the boundary. Canonicalization normalizes data into a consistent representation so that checks cannot be bypassed by alternate encodings or disguised characters. Strong type handling prevents dangerous type coercions or unexpected implicit conversions that change how data behaves at runtime. When these practices are applied consistently, many injection and logic flaws lose their footholds. Parameterized queries represent one of the most effective and universal protections against injection vulnerabilities, which is why you should use prepared statements everywhere. By separating query logic from user-supplied data, parameterization prevents attackers from altering the structure of commands, whether you are interacting with SQL databases, NoSQL stores, or command interpreters. Even when frameworks offer convenience functions, you should verify that they truly enforce parameterization rather than performing simple string concatenation under the hood. Eliminating injection pathways is one of the clearest examples of a coding habit that pays dividends immediately and consistently. Memory safety remains an essential part of secure coding, especially in languages that allow raw pointer arithmetic and manual memory management. Avoiding unsafe constructs and unchecked pointer operations reduces the likelihood of buffer overflows, use-after-free conditions, and other memory corruption issues. Even in memory-safe languages, understanding boundaries, object life cycles, and expensive allocations helps ensure that you do not create hidden exhaustion risks. When memory management is handled deliberately rather than casually, many classes of critical vulnerabilities become far less likely to emerge. Output encoding ensures that even valid data does not become a vehicle for attacks when it is displayed or transmitted. Encoding must be context-aware. HTML output needs escaping for tags and attributes. Headers require constraints to prevent injection of control characters. URLs must be encoded to preserve structure, and logs must avoid inserting content that could mislead analysts or trigger external systems. Encoding transforms user-controlled data into safe representations for the context where it appears. When developers understand this distinction, cross-site scripting, header injection, and log injection issues become far less common. Least privilege applies to code just as much as it applies to user accounts. Processes should run with the minimum permissions needed, whether they interact with files, sockets, system calls, or external services. File permissions should be scoped to the smallest required set, avoiding broad read-write access to directories or logs. External calls should be restricted, limiting which hosts, networks, or commands a process may reach. These design choices reduce the blast radius if the application is compromised and prevent misbehaving code from causing unintended changes. Secrets handling is another fundamental area where disciplined habits matter. Keys, tokens, passwords, and certificates should never be hard-coded in source code or configuration files that end up in version control. Secrets should be retrieved from dedicated vaults, secure stores, or environment bindings designed to limit exposure and rotation complexity. Logging or printing sensitive material should be avoided entirely, and error messages must not reveal details about keys or authentication flows. When secrets are treated as toxic data that must be controlled from birth to deletion, the number of accidental leaks drops significantly. Secure defaults give your software a more predictable and safer posture by enforcing deny by default principles. Explicit allow lists control what inputs, operations, hosts, or content types are acceptable, with all others rejected automatically. Optional features should start in the disabled state, and configuration files should encourage minimal exposure instead of generous access. These defaults ensure that systems remain safe even when new developers, integrators, or operators deploy them without deep security knowledge. Secure defaults act as stabilizers that protect against oversight and rushed deployments. Structured, actionable logging helps you maintain visibility without leaking sensitive data. Logs should capture what happened, when, and why, but avoid storing personal information, credentials, or full request payloads unless necessary and permitted. Structured logs, where fields follow predictable formats, improve searchability, alerting, and analysis by reducing ambiguity. Actionable logs include enough context for support teams or responders to understand failures or anomalies and guide them toward the next investigative step. Logging responsibly balances observability with privacy and security concerns. Unit tests that intentionally cover negative and boundary conditions reinforce many of the secure coding principles discussed so far. Testing extreme lengths, unexpected formats, invalid characters, and failure paths encourages developers to consider how the code behaves under stress rather than assuming perfect input. Boundary tests reveal off-by-one issues, overflow conditions, and subtle shifts in behavior as limits are reached. Negative tests help verify that validation and encoding work correctly, preventing accidental relaxation of safeguards during refactoring. This testing discipline builds confidence that controls remain effective. Peer reviews that incorporate threat thinking ensure that code receives scrutiny beyond functional correctness. Reviewers should ask how input is validated, how authentication and authorization decisions are enforced, how secrets are handled, and how outputs are encoded. Focused reviews look for concrete risks rather than general styling concerns, aiming to surface insecure assumptions and risky shortcuts. Over time, this type of feedback loop raises the team's collective awareness and reduces the likelihood of recurring vulnerabilities. Threat-aware reviews represent one of the simplest yet most effective forms of early detection. Viewed together, secure coding fundamentals form a coherent set of guardrails. You rely on trusted libraries, validate inputs, use parameterized queries, encode outputs, and manage memory and privileges consciously. You safeguard secrets, adopt secure defaults, write meaningful tests, and support one another through focused reviews. This pattern holds across languages, whether you write in C, Java, Python, Go, Rust, or any modern stack. The broader idea is that security emerges not from special tools, but from consistent, careful habits that catch mistakes before they scale. To close, choose one secure coding rule that you know will immediately strengthen your daily work and add it to your personal or team checklist. It might be eliminating string concatenation in database access, enforcing output encoding for HTML contexts, or reviewing configuration files for hard-coded secrets. Select one habit, apply it consciously in your next code change, and use that experience to refine your checklist. Over time, this incremental approach shapes a secure coding culture that grows naturally rather than through long lists of mandates. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.